Thank you very much. So let's move on to the next speaker. Next speaker is Dr. Thomas Funck. The title of the presentation is Decoding the Laminar Chemoarchitectonic Contribution to Brain Function in the Macaque.
I'm Thomas. I'm very grateful to have the opportunity to present to you all today. And so today we're going to talk about some work that we've been doing to build high-resolution atlases of neurotransmitter receptors in Macaque, and then starting to relate these receptor distributions to brain function. And I have no disclosures. So the data that we're working with comes from Jülich Forschungszentrum and was originally collected by Nicola Palomero Gallagher and Carl Zillis. So these data are autorator graphs. They're 2D images that have been acquired post-mortem, and they quantify neurotransmitter receptor distributions in the brain. This method has a lot of big advantages. Notably, it's quantitative. It lets you visualize multiple receptor systems within the same subject, so you can see how receptor patterns co-vary within an individual. And also the resolution is very high, so 50 microns about. So the data sets cover many different neurotransmitter families, and has been acquired, similar data sets have been acquired in human macaque and rat, although today we're going to talk about the macaque. So you can see this data is in 2D, and we'd like to be able to do 3D whole brain analysis with it. So there's a big challenge to getting this data in 2D back into its original 3D spatial embedding. So there's a lot of challenges related to that. If I'm starting to get gray hairs, it's partly due to these challenges. One is the problem is that for autoradiography, you can't chemically fix the brain before you extract it from the skull. So when you pull it out, it's still all soft and it kind of like deforms. So you have to correct for these special deformations during the reconstruction process. Another issue is that when you put all these receptors into a volume together, they have extremely heterogeneous pixel intensity distributions, and so it becomes impossible to use traditional methods to align the receptor volume to the anatomic volume that you use to correct the deformations. Finally, because we are acquiring multiple different images from multiple receptor systems within the same subject, for a given receptor, there's always going to be gaps between sections acquired for that receptor, and so if we want to create a whole brain volume, we have to be able to fill in those gaps in some way. So I've been working on a pipeline which will shortly be published, hopefully, and it's called Brain Builder. So it's an automated pipeline for reconstructing sparsely sampled multimodal 2D brain sections into 3D. So it's available on GitHub if anybody's interested. I won't go through all the details. I'll just mention two important points. One is work that I was very fortunate to be able to do with Conrad Wagstill at King's College. So basically we developed a neural network that would segment cortex from 2D sections. But this neural network was trained completely with synthetic data from one brain, from the big brain. So we generated a bunch of synthetic data, trained the network, and then validated it on manually drawn labels in the human and the macaque. There is a mistake there for some reason. The dice scores there should be 0.93 for the human and 0.91 for the macaque. I don't know what happened there. So in any case, that is to say that it generalizes very well to actual data from autorator graphs and even generalizes to new species that it's never seen before. What this allows us to do is take the receptor volume that you see here and then transform it into a binary, a gray matter volume that is then much easier to align to some kind of reference template. If the gray matter volume is still a little bit jaggy, that's just because of the very sparse sampling of the receptor data, and that's kind of hard to get around. So coming back to the problem of estimating receptor densities between acquired sections for a given type of receptor, we've developed a few techniques, and we have a new one that works very well. It's quite simple. Basically, all you have to do is use ants to calculate a nonlinear alignment from one section to the next section in the anterior direction. And so this creates a deformation field in the forward direction and a deformation field in the inverse direction. And then we can then scale those deformation fields and use them to transform the first image in the forward direction, the second image in the inverse direction, and average them together. So basically, we're doing a linear interpolation through the nonlinear deformation field. And thanks to this, we can actually create the volumes that you see here. So it looks pretty good. And sort of as a proof of principle, you can look at the muscarinic M2 receptor, which is highlighted in the primary sensory regions. So you can see the auditory region coming up there and the somatosensory. And I'll also point your attention to the 5-HT1A receptor that we'll talk a little bit more about later on. So these brains were aligned to the MeBrains template. And there are three 3 left hemispheres averaged together, and these were reconstructed at 250 microns. And so big thanks to Meichi, who's here, and Camille and Nicola, because they've helped a lot in QCing all of this and helping get it to this stage. And also Nicola collected the data. So now that we have the volumes, we can begin to analyze it. And the approach we've taken so far is to project the volumetric data onto cortical surfaces spanning the depth of the cortex. And then we bin these layers into 3, you could call them pseudo layers, superficial, middle, deep, each covering a third of the cortical depth. So a big caveat here is that these are not identical to cytoarchitectonic layers or even chemoarchitectonic layers. They're just a coarse approximation, but they're still useful to get us off the ground. And so the first approach that we've taken to sort of getting a handle on how these receptors might covary together, how they covary together, is to look at the variation of the receptor fingerprints. So if you imagine at each vertex you would have a vector with the z-score density for each receptor, and then first we calculate the standard deviation and look at how it changes across the layers. And the fact is it doesn't seem to change very much. The standard deviation is pretty much the same across all the layers. It's very high in the occipital lobe, visual cortex, and in the medial temporal lobe. So it seems pretty consistent. However, we see something very different with entropy. Entropy is also a measure of variation, but it's insensitive to scale. And so what this shows us here is that the receptor distributions in the superficial layers are much more surprising, as it were, are much more difficult to predict. And that decreases as we go to deeper layers, which I think kind of makes sense. It suggests that the receptor distributions in the superficial layers, more superficial layers, have a more complex distribution, which somehow underpins neural information processing. Then we also looked at gradients, as one does. We used PCA because it's simple and robust. And if you look at the first component, I think it very clearly shows the very familiar now primary sensory to transmodal association axis. But what we see, though, is that, I think it shows up here, is that as you go deeper, it sort of starts to fade. And so it shows that the structure of the receptors or the covariance of the receptors is changing as we go to deeper layers. Component 2 seems to have some elements of the default mode network, like the precuneus, but also seems to segregate occipital lobe from frontal cortex. So this one, I think, warrants more investigation. It's very interesting. And what's also really cool here is that if you look at the explained variance of both components together, we have between 75 to 85% explained variance, which seems very high. And so it really suggests that receptor distributions are governed by low-dimensional patterns of organization. So before we were looking at fingerprints, so all the receptors together, but there's also a question of how do the individual receptors vary through the layers. And so we wanted to try to quantify the uniqueness of the receptor distributions in the different layers. So we have 2 different metrics for doing that. One is just entropy again, the entropy of each receptor over the surface. And then we also looked at linear dependence, so you basically just take one receptor map and regress it on all of the others. And what we see very clearly is that 5-HT1A that I had mentioned before jumps out quite obviously. It has a very unique receptor distribution pattern. What that means, I don't know. I think if anybody has any insight into that, I'd be interested in talking about it. But I think it definitely warrants more investigation because it suggests that 5-HT1A is playing a very particular role in information processing. And we see that uniqueness also across all the layers. It's not just the superficial layers. So now that we've sort of characterized some of the patterns of the receptors that we've seen, we can also start to try to link them to brain function in some way. And one way that we've done this is to look at functional networks defined in the Macaque and just take the average of the receptors, find the receptor fingerprints for each functional network. And so we see that here in the superficial layers, you have a much higher receptor density, which I think makes sense and is to be expected. But we do have interesting patterns where, for example, the ionotropic glutamate receptors, kainate and AMPA, seem particularly densely located in the insula and opercular networks, as well as the limbic networks. And this cuts across the layers. Even in the deeper layers, you have more AMPA. I don't think I have a laser pointer, but yeah. So you'll have to take my word for it if you don't see it. So even in the deeper layers, kainate is very strong. Finally, We wanted to try to link the receptor maps to maybe more specific domains of brain function. And unfortunately, we don't have easy access to that kind of data in the macaque. But we do have that in the humans through NeuroQuery, where we can define average human fMRI activation maps. And so we did that for several functional domains. And then we used Ting Xu and Karl-Heinz Nenning's cross-species transformation, which actually I think we just heard about in the previous talk too, to transform the macaque receptor data into human space, which you can see here for the M2 receptor. You see it more or less, it works pretty well. And then we could do a regression of the functional maps onto the receptor maps. And so here we have the significant covariates in those regression models. And what it shows basically is that the middle and superficial layers have a much stronger relationship to the functional domains. So it's not just that receptors are denser in the superficial layers, but also in the, they also have the spatial distribution of those receptors links more closely to the functional maps. So some conclusions and takeaways. Receptor distributions in superficial layers are more unpredictable. They have higher entropy. Receptor organization is governed by two low-dimensional patterns that seem to account for approximately 80% of the variance, with a strong sensory association access, especially in the superficial layers for component 1. 5-HT1A has a very unique receptor distribution, indicating a potential unique role in neural information processing. And finally, receptors in the more superficial layers are not only more dense, but are, in terms of their spatial relationships, are more clearly linked to brain function. Now, that doesn't mean that, for example, like GABA didn't show up as significant. That doesn't mean GABA is not important in brain function, right? It's just the spatial maps. If anybody knows somebody who would be interested, we are looking for a postdoc to push this analysis really to the next level. So we've been doing linear modeling here, but now we want to start doing whole brain modeling with neural mass modeling. So if anybody knows somebody who'd be interested in the position, please reach out. So this will be at CMI in New York City. And so thank you to everyone involved in this project. Of course, Nicola and her team, Meichi, Camille, Lucia, to Ting, of course, who I work with at CMI, and of course, PJ, who's right here.
So we have time for just one question. Yes.
It was probably just more a statement of how beautiful that work is and how important I think it is for the field to really embrace this complexity. One quick comment and then one quick question. 5-HT1A receptors are fascinating, right? They're a GI-coupled receptor. They often sit on the axon initial segment of pyramidal neurons. So if you activate those, you're actually going to make it harder for the cortex to communicate with itself or to actually have messages leave. So we should chat about that at some
come
point.
to the poster.
And my question is, have you thought about looking at covariance patterns? So seeing whether or not the expression of one receptor in one location co-varies with the expression of another and individual differences?
I haven't, I mean, I guess in some way PCA captures some of that, but PJ actually is working on that, or wants to work on that. So yeah, you can come talk to us.
Let's get a coffee and chat.
And sorry, I forgot to mention something. All this data will eventually be made public once we've QC'd it and are happy with the quality of the reconstruction and all that. So everybody will have access to it.
Cool, all right, let's chat.
Sorry, so because of time, we have to move on. So thank you very much.